Assalamu alaikum. It's our 19th lecture on advanced electromagnetic field and waves, and in this lecture we have to start our new chapter which is about radiations. Okay, to start, let's start with an AC source. So let's suppose this is our AC source, which has this positive polarity and this is negative polarity. The current is flowing in here is in this direction, and the direction of current is in the outward direction. Okay, now let's suppose because your current is going, so the direction of current is like this. Okay, like clockwise direction, and for reversing the direction of the current is like this. Okay, in the anti-clockwise direction. Now what would happen, because this field interact with this field, and this is in this direction and this will in this direction, and their fields cancels each other, so there is no effect. Okay, so what if we have to do some effect in that? Our sources are charge density and you can say the current density. Okay, so if you bend your loop like that, so here what would happen, you can see now your current is flowing in this direction. Okay, like in clockwise direction, and in this your current is flowing in this direction in anti-clockwise direction. Now they don't just cancel each other. Now by changing current produces change in magnetic field, so you can see here is a change in magnetic field produced, and again change in magnetic field produces the change in uh, uh, electric field, and this is so on, again produces magnetic and again produces electric field. Similarly case here. Okay, now your field is start propagating, going into electric field, going into magnetic field. Okay, so as we know that the relation del cross B, which is equals to JC plus partial D by partial T, means change in electric field produces change in magnetic field. But in this scenario, your JC has done his job, because JC conduction current is basically here. Now if you can see, if there is no displacement current, then how should, because this factor is not explained by only amperes, so so only Maxwell's. Okay, so Ampere Maxwell's law, this states that the change in magnetic field is basically the sum of the conduction current and the displacement current. So this is how. So conduction current done his job. Now the only field that is propagating is this vector, which is the displacement current. Okay, so this is very important. So let's start. So in this chapter our sources are, let me write here. Our sources are two. First is charge density, and our second source is current density. Because you know that in all previous lectures we are taking current density and charge density equals to 0, but in the radiations this chapter we are not letting as 0. We are taking their charge densities as well as the current densities. Understood? Okay, so let's start. So if our charge density is, and current density is denoted by J, and charge density is denoted by rho. So if these are included, so their space-time equation can be written as, for the case of charge density, your rho of xt should be written as rho of x, which is the space part, and for the time part it will minus iota omega t. Okay, and whereas your current density can be written as in space time as, okay, j, which is the current density, x, which is space part, and their time part can be written as e power minus iota omega t. Okay, so these are your main equations. Now what you have to do, you just have to use the same equations, and you know that del cross B basically equals to, because here you just have to multiply by Initially you know that your del cross H basically equals to what? This is equals to JC plus uh, partial epsilon partial E by partial T, because you know that D is basically equals to epsilon and E. Okay, by putting the value of D, which becomes this. Now you just have to multiply whole equation by mu. So you also know that mu H is equals to B. So when you multiply mu with whole equation, so mu multiplied by H becomes del cross B. So your del cross B becomes equals to, um, here you can see, like it becomes, and here it becomes mu JC plus mu epsilon partial E by partial T. Okay, so here let our this equation as equation A, and you know another equation of curl of electric field. This is curl of magnetic field del cross H, which is equal to displacement plus conduction current plus displacement current, and del cross E basically equals to, you know, that change in magnetic field, which is minus partial B by partial T. This is your equation B. Okay. Now you know that, first of all, Gauss's law. We already have a detailed video on Gauss's law. It basically tells you the, you can say, the divergence of magnetic field equals to zero. So if divergence is equals to zero means no distribution. If your divergence is basically equals to zero, it basically means your wave is propagating in curls. Okay, if your divergence is zero, it basically shows that your wave is propagating in the curl direction. Okay, so there is another factor B. It can be written as del cross A. Okay, so basically this A tells us about the, you can say it is the magnetic vector potential. Okay, this A is basically the magnetic vector potential. Now what you have to do, as you know your equation, which is this, your curl of electric field, what you have to do, you just have to put the value of B in equation B. So your del cross E becomes minus partial by partial T, which is as it is. Now you put the value of B, you know that the value of B is del cross A, as I mentioned here. Okay, now take del outside, and what it becomes, minus partial, it becomes minus del, sorry, minus del. Okay, minus del becomes outside, and it becomes partial A over partial T. Understood? Now what you have to take, you have to take this to this side, so it becomes del cross E, which is the curl of electric field. This comes here to, it becomes positives del partial A divided by partial T, which becomes equals to 0. Okay, now what you have to do it, you see the, here is a common factor, which is del is common, so you have to take del common. So after taking del common, what's left inside, you can see inside is the E plus partial A divided by partial T, which becomes equals to 0. So here you know the property. Okay, so here is cross, so here is also a cross. Okay, you are taking common cross, del cross. Okay, here is also cross, when this del comes outside, so here is also cross, so you are taking del cross common basically. Okay, so after taking common, so if cross product of two are zero, basically what it means, if curl of two things are zero, so basically it means the gradient, it is basically the gradient of any scalar. Okay, So if this is gradient of any scalar, so we can say that this E basically equals to minus delta psi. This psi is, let's suppose, is a scalar. Okay, understood? So if the curl equals to 0 means it is basically the gradient of any scalar. So if this is gradient of any scalar, so you have to become equal to this. So as your equation is this, so after what it becomes, so because your you can see here curl of this equals to 0 means this factor is gradient of scalar, and as I told you, gradient of scalar can be written as this, so this becomes equals to this. So what you can be write as E plus partial A divided by partial T, which becomes equals to this, which is minus del psi. Understood? Okay, now move this to the other side, so your E becomes equals to minus del psi minus partial A divided by partial T. Okay, now what you have to do, you have to put the value of B and E. So as you know, the value of B is del cross A, and the value of E, which we just find here, you have to put this in the equation. As you know that there is an equation which I wrote here, this equation. Okay, you have to put in this equation. So as you know that your this equation is del cross B, so it becomes del cross the value of B, which you know that del cross A, so it becomes del cross A here. Okay, and equals to mu as it is, and conduction current as it is, and plus mu epsilon as it is, partial E by partial T. Okay, means partial by partial T as it is, and you put the value of E, which you find here, minus del psi minus partial A divided by partial T. Understood? Now you have to just take time derivative, so it becomes del cross del cross A. You have to use your identity here. Okay, it becomes equals to mu J plus mu epsilon partial by partial T minus del psi, and minus mu epsilon partial square A divided by partial T square. You just multiply this by this and this by this. Okay, now what you have to do, you have to apply your uh, vector identity here. You already know. Okay, we already applied vector identities many times, so you have to apply vector identity here, and it can be written as how, and this can be written as del dot A minus del square A. Okay, which is equals to same as it is mu J minus, it becomes minus, so minus mu epsilon delta partial phi by partial T. This phi is, you know that it's basically a scalar, gradient scalar, minus mu epsilon partial square A divided by partial T square. Understood? Let's further proceed from this equation. What you have to do, just move this expression to the other side of the equals to sign and take del common to the other side, and this remains here, and move this. You can move this equation, sorry, this equation to this side. So how it becomes minus del square A as it is, so minus del square A as it is here. Okay, and this becomes here, so it becomes positive, so it becomes positive mu epsilon partial square A divided by partial T square. Okay, sorry, this equations came this side, so this becomes like this. Okay, and equals to sign this mu j as it is here. Okay, and the other factor, as I told you, you have to take this expression to the other side and take del common. So here is del and here is del, so moving other side it becomes minus, so you have to take minus del common. So inside left is del dot a, so inside left is del dot a, and here is what left, because you take minus common, so it becomes plus mu. Okay, so it becomes plus mu silent and partial psi by partial t as it is, and this del you take common, so this is the final equation it can be written as. And there is a property, you know, that Lorentz gauge, which basically tells us that your del square a basically equals to minus mu sin L partial phi by partial t. So this is basically the expression for Lorentz gauge. Okay, so this tells us about del dot a becomes equal to this. So let's suppose if del dot a is this, so here is del dot a. If I put the value of del dot a is this, so you can see this is similar to this, so basically this cancels with this, because the value of del cross a is negative of the same factor. Okay, minus mu epsilon partial psi by partial t, so here is plus mu epsilon partial psi by partial t, so both cancel, so this terms becomes goes to 0, so del dot 0 becomes 0, so you will only left with these terms equals to mu j. So your final expression can be written as minus del square a, okay, minus, how you can write, here is a property which I have to mention here. First let me write it as it is, plus mu epsilon partial square a divided by partial t square equals to mu j. That's it. Okay, now here, because we are taking a time space time, so e power minus iota omega t is the time factor. Okay, and if I take derivative, because here is the double derivative I need, so if I take the first derivative d by dt of e power minus iota omega t, so I get first of all the same e power iota omega t and the derivative of minus iota omega, which is the minus iota omega. If I take the double derivative d square by dt square of this, so what I got, if I take the double derivative, okay, so I should left with, you can see here, so double derivative of this, so here it becomes minus again minus iota omega from here, and then after taking again derivative of this, it again gives you minus iota omega and e power minus iota omega t as it is. So minus minus becomes plus iota square omega square, and iota square, you know, it's basically equals to minus 1. So answer is minus omega square, and this is basically time part we just ignoring. Okay, so here your partial square by partial t square becomes equals to minus omega square. Okay, and you also know that here, which is written as, you know that your mu epsilon can be written as, let me show here first, just write this, which becomes equals to minus delta square a. Okay, because this partial square by partial t square becomes minus omega square, so minus omega square mu epsilon a as it is equals to mu j. Okay, now what we can see here, if I take minus common and move other side, so it becomes del square a plus omega square mu epsilon a equals to minus mu j. And I know that this factor can be written as which factor? This factor, omega square mu epsilon basically equals to k, because you know that k square is basically equals to omega under root mu epsilon. So if k becomes equal to omega square mu epsilon, which is this, so your final expression can be written as del square a plus k a equals to minus mu j. So this is the final solution of this, which I mentioned you, a, which is the magnetic vector potential. Okay, this is the magnetic vector potential general solution. Okay, this is non-homogeneous because this is the source term, this. Okay, this term is known as source term, this j, this is the source. So if there is source, so this is non-homogeneous equation, non-homogeneous equation. Okay, so this is non-homogeneous. But if you want homogeneous equation, what in homogeneous your source term becomes equals to 0, means this term equals to 0. Now then your del square a plus k a becomes equals to 0. So this is your homogeneous equation. Now let's conclude our today's lecture with a small topic, which is the green function. So simple trick in this green function, that there are two terms, like you know that first of all let's take Laplace equation. So first of all let's take Laplace equation. You know that your del square phi, which is equals to minus rho by epsilon naught. This is your Laplace equation. In this upside is basically the source term. I already mentioned you that this is the source term and this is the unknown term. Okay, this is the source term and this is the unknown term. And let's take another example of another equation which we just derived for magnetic vector potential. So which is, you know, that del square a plus k square a equals to mu j, which we just derived here. So in this also I told you this j is basically the source term. Okay, this j is basically the source term, and this factor is basically the unknown factor. What if you want to find the green function? Okay, what if you want to find unknown? Okay, what if you want to find the unknown? So to find the unknown, what we have to use is the green function, and the formula for this you just have to remember that integration of your green function multiplies by the source. Just multiply the green function multiplies by the source. So every equations have their own green functions. You must have to remember there are few, there are not the many functions, there are just few, like for the case of Laplace, which I mentioned here, this the green function of this Laplace can be written as 1 minus 1 by 4 pi epsilon naught r square. This is the green function of this Laplace. Okay, and the green function of this magnetic vector potential is you can write it as mu naught divided by 4 pi r. So these are some green functions you can remember. Okay, so what if I want to find the green function of our Laplace equation? So just I have to multiply my green function, which is this, multiply by source, and source I know that this is minus rho. So it becomes what? I have to find the unknown, which is in that is psi. So my psi becomes equals to my green function. Green function is this, minus 1 divided by 4 pi epsilon r square. Okay, and multiplies by sorry, there is an integral sign here, multiplies by source, and source I mentioned you, which is minus rho. So your unknown psi becomes equals to integration of rho divided by 4 pi epsilon naught r square. So this is how you can find the green function of an unknown. So let's again find the green function of our this second equation, which is this vector magnetic vector potential. So as you know that if here is the unknown is which a, if I want to find a, which is become equals to under root the green function, as I mentioned you that the green function of this is this mu naught divided by 4 pi. Okay, r is basically the position. Okay, so position can be written as x minus x prime. Okay, this position can be written as x minus x prime, multiply by their source term, and in this the source term is this j, because I take x minus x prime, so it have to be integrated over dx cube. Okay, so you can see here that here we take the common outside, so we will left with, because mu naught and this 4 pi are the constants, we have to integrate our volume. So you can see it becomes j divided by, because this is a relationship like Coulomb's law, so we have to integrate our volume. So here is one position, so inside it becomes x minus x prime cube dx cube. So this is how you can find the unknown with the help of the green function. Just remember that these term is so called as the unknown terms, like this is unknown and this is unknown, and these terms like charge density and current density could be considered as the source terms. So if you want to find unknown in this, which unknown is psi, and in this equation the unknown is a, so just have to integrate or green function multiply by this source term. Green functions, every equation has their own, you have to remember. Okay, some of I mentioned here, like for the Laplace equation the green function is this, and for this magnetic vector potential the green function is this. Just multiply with the source term, you will get your unknown. Okay, so that's all for our today's lecture number 19 on advanced electromagnetic field and waves. We will upload more interesting lectures for this course. Till then, stay connected with us. If you have any query, you can just leave the comment below. In our coming video, we will discuss about the coordinates, different coordinates like Cartesian coordinates, cylindrical coordinate system, and we have to also discuss the spherical coordinate system. Okay, so that's all for today's lecture. In this, we just started our new chapter, which is the about radiations, and we successfully drive the magnetic vector potential, homogeneous as well as the non-homogeneous equation. You already know, if your source term is zero, then your equation becomes the homogeneous. And then we move on towards the green function. Just you have to take the integral and multiply your green function with the source term, you will get your uh, the unknown term. Okay, so this is how you can find the unknown term with the help of a function which is so called as the green function. This is one of the easiest way to find the unknown. Okay, so thanks for watching this video. Till then, take care. Allah Hafiz.